Welcome, everyone, and thank you for attending today's Quantum. This year's Quantum is organized by I'll begin with a land acknowledgement. The University of Washington acknowledges Coast Salish peoples of the land which touches the shared waters of all lands and tribes of the Squamish, Tulalip, and Montezuma nations. The lab also acknowledges that we live and work on the ancestral lands of the Squamish people, the first people of Scotland. Now to introduce our speaker. Luoliang Xu is a postdoctoral fellow in the Center of Limnology at the University of Wisconsin-Madison. He holds a PhD in environmental and ecology science from the University of Maine. His research interests focus on fishery stock assessment and management. He is currently working on evaluating the impact of climate change on freshwater fish productivity. Luoliang will take questions after the talk. And thanks everybody for coming today. Big thank you to our speaker for sharing your work with us today. And with that, it's my pleasure to turn it over to Luoliang.
Well, thank you very much. Thank you for the introduction. Thank you for pronouncing my name so accurately. I'm not that used to. Good afternoon. Good afternoon, everyone. So today I'm very excited to share some of the results from our recent study. And the title is Small Rains and Big Losses, Asymmetric Impacts of Climate Change on Preferred Thermal Habitats of Inland Lake Fishes. Well, the concept of winners and losers in response to climate change is well recognized. So climate change is transforming animal habitats across diverse ecosystems, leading to profound impacts on the resident species. And presumably, animals benefiting from the expansion of their preferred habitats often thrive as winners, and those unlucky who lose preferred habitats with the same ecosystem will become losers. So as global warming has happened and will continue, it is expected that warmer habitats are generally will expand and the cooler ones will generally to shrink. And the change in thermal habitat are particular concern for freshwater fish. So let's compare it with marine species. So marine species usually have the chance to shift latitudinally to seek more suitable thermal conditions in response to warming. The figure on the screen shows example of 3 marine fish, cod, anglerfish, and snake blenny in North Sea. And their shifting pattern is pretty much representative of the general shifting pattern of global marine fish, that is a forward shift in response to climate warming. In contrast, freshwater species must adapt in place due to their restricted environments. They cannot simply relocate to another lake, I guess. So this spatial limitation poses significant challenges for these species. And 2 very intriguing studies published, one is in Nature and the other in Nature Climate Change, underscores the contrasting destinies for marine and freshwater fish on extreme heat conditions. For marine demersal fish, heat waves have surprisingly not been a dominant factor driving change in their populations. Probably the vastness of the ocean and the ability of these fish to move to cooler waters may offer them a temporal refugee from rising temperatures. On the other hand, the situation is starkly different for freshwater fish. These fish confined as they are in a limited and often isolated environments like lakes may face catastrophic die-offs if thermal extreme hit their habitats. So basically, the climate temperature is forcing the freshwater fish species to either adapt to the change conditions of their cousin habitats or face severe consequences. Well, assessing the change in thermal habitats for resident fish species needs data beyond surface lake temperature and annual average. as temperature rises, the thermal conditions within lake experience varying degree of change across different depths and seasons. So shaped probably by the distinct lake features like morphology or like water clarity. So if we only use surface temperature, it will overlook the thermodynamics within lakes. So depending on species, it may find their, like the figure shows here, it may find their optimal habitats at certain depths during specific seasons or across various depths during particular times of the year or vice versa. So the data beneath the surface are important in assessing their habitat. So luckily, thanks to the lake temperature modeling group of the project, we got this important data released last year. So the data set contains daily lake temperature profile for the past 4 decades also, and for more than 10,000 lakes across the Midwest US. And the model used GLM model. So GLM here does not represent generalized linear model, but general lake model. So it is a mechanical model. Yeah, I just want to highlight that in case it is misleading. So this figure shows the key process that affect lake temperature, it including like the evaporative cooling. This is a process that usually make the lake surface temperature cooler than the atmosphere temperature above it in summer. And it also includes the surface heating, and the wind stirring will facilitate the surface mixing and also probably affect a little bit the deep mix. And this model incorporates meteorological observations. So the like the temperature, humidity, wind speed in the past 4 decades. So that observed and very precise data used in informing the model. So ideally, if we have equipment in the lake to, if we have equipment in the lake to record the temperature in different layers, those observed temperature could be used to calibrate the model. And except for like environmental data, another piece of data we need for the analysis is the geographic range of the fish species, so that we know which lakes were within the certain species range, which are not. So the range of fish species in this study were compiled from a variety of sources, and these data were consolidated at the watershed level. So take a Y spatial range map as an example. We know that in those shaded areas, Y has been observed and recorded, but we cannot, of course, ascertain that Y existed in all the lakes in that watershed. But to our knowledge, this data set provides the most detailed and comprehensive spatial information on species existence across such a broad scale. And the third data we need is, fish preferred temperature. How do we define the fish preferred temperature? So here we used the most relevant and widely available metric, that is final temperature preference. So the final temperature preference is the fish gravitate toward inner thermal gradient. So basically how it is measured in lab is that we have a huge tank with interconnected compartment with different temperature, just create a temperature gradient, and you just put a bunch of fish into the tank and observe where the concentrate. So the FTP is final temperature preference is quite close to the OPT, the optimal temperature for growth. So, but as I mentioned before, because FTP is more readily determined in a laboratory setting compared to the optimal growth temperature. So it provides more consistent results across a wider range of species. And it is theorized that this temperature represents one that fish would instinctively seek out in their natural environments, if not constrained by other environmental factors. And here we have 60 species, and they are categorized into 3 different thermal groups based on their FTP. The FTP below 19 was categorized as cold water species. Between 19 and 23 is cool, and above 23 is warm water species. So to gauge their availability of preferred thermal habitats over time, this study focused on calculating the number of days per year when a lake temperature profile included their FTP for each species. So we believe that the change in days is sensitive enough to reflecting whether the lake's overall thermal habitats are moving towards or away from species optimal, since other metrics are that influence their habitat availability are relatively stable, like the size of the lake or the volume of the lake. So we use preferred days. And the method here is quite straightforward. There's I think no quantitative difficulties, except you need a very high performance computer with large RAM to deal with the big data. So first we match the lake location with the fish spatial range, and the lakes whose centroid latitude and longitude lie within the fish range will be included. If it is not, it will not included to calculate preferred days for that particular species. And then we calculating preferred days and compare recent period with earlier baseline period. The recent period is 2001 to 2021, and the baseline period is 1980 to 2000. So 21 years. Well, here is the results. So on average, species that prefer cooler temperature lost preferred days, while those prefer warmer temperature gain preferred days, which is not surprising. The species that prefer warmer temperature are winners in the face of global warming, not surprising. But notably here is that the magnitude. So the magnitude of decrease in preferred days for species that experiencing a decline was more profound than the increase for those that experiencing a rise. So the average reduction is 7.5 days per lake, but the average increase is only like 2.8 days. So this is what we call big loss and small gain in the title. And this is show the spatial and frequency distribution of the change in preferred days for species in different thermal guilds. And the color here, both in the points and in the bars, represent the magnitude and the directions of change. So for cold water species, it experienced a widespread reduction in preferred days. And we noticed that lakes showing a high rate of decrease are actually scattered across this study area instead of like showing any like latitudinal patterns. And the results for cool water species were bimodal. And we observed that the relatively large increase in preferred days occurring in the Michigan, northeast Wisconsin, and northeast Minnesota. And warm water species saw a general rise in preferred days in most lakes, but we did not see a very rapid increase, at least not a level of decrease we see for cold water species losing preferred days. So nothing like more than like 20. So I think this is pretty much the results, but we take a little bit further to try to understand maybe the reason behind these phenomenon. And we come up with 3 kind of hypotheses and test them. And the first hypothesis come into our mind is that probably because of the influence of geographic distribution difference of the species, because we calculated preferred days to only the lakes within a species geographic range. So this raises the possibility that lakes within the range of cold water species, probably more north, might have warmed more rapidly, and that lead to a sharper decline in their preferred days. So to evaluate this hypothesis, we just recalculate their preferred days and regardless their geographic differences. So if that in that case we lowering their difference in geographic distribution and range, it still have the similar pattern of big loss and small gains that will imply that the distinct geographic range of the species are not the underlying cause for the phenomenon. So we did that, and here is the results. So we actually see the similar pattern, actually the same pattern, general pattern, a large reduction in the number of days featuring cooler water temperature and a lesser increase in the number of days with warmer temperature. So that means, well, their geographic difference is not okay. It's not a reason. So the second hypothesis is maybe it's related to the seasonal availability of preferred days. So in temperate area, if you are a warm water fish, you probably cannot enjoy it very much because the temperature you prefer is very high and probably could only happen in certain seasons like in summer. So even with the climate warming, that will increase your preferred days, but it only limited to hottest summer months. And in contrast, cold water species face reduction probably over more prolonged duration throughout the year. So we assess this hypothesis by calculate the monthly change in the number of preferred days. That lake contained the midpoint temperature for cold, cool, and warm water species, that is 15, 21, and 27 degrees Celsius. So we also evaluate for all lakes in their study area, and we found that a substantial reduction of cold days occurred from May to August, and with a minor and to moderate increase in March and April and October. And cool days declines in July and August, but it is compensated by the increase in June and September, and finally it get increase annually. And for the warm water species, as we expected, their huge increase only happened in July. So, and this also this kind of associated with lake's seasonal thermal stratification and mixing dynamics. So these violin plots represent the monthly average temperature from the whole time period for each of the lakes in this area. So the red portions indicate the average highest temperature, and blue indicate the highest and lowest temperature of each lake. So like in the cold months like January, across the landscape, the temperature range is quite low, but they expanded substantially in warmer months, such as like in July. So it's because some of the deep lakes, even in the very hot July, they still have some cool temperature in their deeper layers that could potentially be the habitat for cool water species. And warming will reduce them, of course. So warming reduced the preferred temperature for cold water species across several months, and warming only increased preferred days for warm water species during like peak summer. And we believe this contribute to the observed asymmetry in the thermal habitat changes. Well, the third hypothesis, is related to like maybe the stronger mixing, vertical mixing waters diminish the thermal habitat diversity. So this figure is a simplified diagram illustrating the two patterns of lake temperature profile shifts due to warming. So temperature in different layers may increase with different speeds. And if the highest temperature is increasing faster than the lowest temperature, it will lead a more profound expansion of the temperature spectrum at warmer end compared to the lower end, compared to the loss at the cooler end. So it will provide net gain of the thermal diversities for species prefer distinct temperatures. And conversely, if the lowest temperature within a lake is increasing faster than the highest temperature, that means the temperature lost at the cooler end outweighing the gains at warmer end. So this reflects a stronger overall lake temperature mixing and hence the net loss of thermal habitats diversity for fish prefer different temperatures. So we just checked the proportion of net gain and net loss temperature and found that the vast majority of the lakes in this area exhibited the net loss pattern, which means the lowest temperature is increasing faster than the highest temperature. And well, interesting, as you can see that the net gain lakes were predominantly located in Michigan, the northeast Wisconsin, and the northeast Minnesota. So this coincide with the areas that showed a substantial increase in preferred days for cool water species. And this is probably influenced by the prevailing stronger winds. So here above the lake surface, we found that 99.6% of the lake surface are experiencing a stronger wind during the past 4 decades also. So the stronger winds may increasing the mixing and increasing the thermal exchange vertically and will reduce the thermal diversity or increase the homogeneity of thermal range. And we also find that the the lake's response to the stronger wind is contingent to the depths and their clarity, water clarity. So the net gain lakes have on average deeper depths and lower clarity than the net north lakes. So deep lakes regularly stratify during summer, which could isolate deep water layer from the surface and significantly lowers the vertical turbulent diffusive transport. So, and additionally, the low water clarity, which causes high light extinction, further causes increased heat absorption and storage in the layers that near the surface. So it will increase the temperature difference between surface and deep water layers. But in contrast, the shallower ones with clear water will, more prone to the wind mixing and vertical transport of heat, and promoting more uniform heat distribution throughout the water column, and which aligns with the net loss scenario. Well, and there are probably other factors. So here, the study we focused on the change in daily availability of thermal habitats across different species, but other factors could intensify these asymmetric impacts. For example, this is another asymmetric, very famous asymmetric curve describing the relationship with temperature and the fish performance. So typically, the fish performers exhibit a kind of moderate rise with temperature below the optimal point, but it will experience a very sharp decline when temperature exceeded. So consequently, actually, each preferred days lost by cool water species is because the temperature too warm for them. That could have a more severe negative impact than the incremental benefits warmer water species gain from additional preferred days. So that is one factor that could intensify the asymmetric impact of climate change on freshwater fish species from different thermal guilds. And another question raised is that, do winter warming matters to fish growth? Because the study shows that actually it does not have it does not have a direct impact on increasing the preferred days, because the temperature generally in winter are too low, and it is also believed that for fish in the temperate in the lakes in the temperate area, the fish does not grow in winter because the temperature is too low. But we think that actually the indirect impact of winter warming could be important. We haven't tested that yet, but the reason of winter warming is important is that for the lake with seasonal ice, the early thawing of ice caused by winter warming may lead to a premature warming of lake water. So this probably will effectively advancing the onset of spring temperature or prolonging the summer season, which can influence the growth condition of fish. So given the importance of ice phenology in regulating seasonal lake temperature, winter warming could still be the key driver. I think maybe this need further research on its indirect impact on altering fish growth thermal habitats. Well, what's the management implication of this study? So we know that climate change has created winners and losers in various ecosystems. And the success of winners may not offset the losses of losers in kind of maintaining high quality ecosystem services. So fishing opportunity, of course, the vital services provided by freshwater ecosystem probably may face net losses as fish community changes. So in freshwater recreational fishery management, the resist accept direct framework is widely discussed as a probably effective tool for managing freshwater fish species. So this approach actually, three strategies: resist, or accept, or direct. So in this framework, I think most of the marine commercial fishery management are in the resist category. All the rebuilding plans we want to implement is just to resist the decline of the fish and the fishery. But here we are talking about maybe we can accept some of the declines of freshwater fish species, as we know the lake no longer provide natural sustainability for them. And even with docking and even with the measurement of catch limit, we cannot really change that. So we probably could accept that. And then the third one is directing. So we could intentionally direct the fishing efforts from cold water species to cool and warm water species, with assume that the latter will fare better under warming conditions. But it should be, I think the manager should be keep that in mind, that the overall reduction in fishing opportunities due to the decline of cooler water species might not be completely offset by the increase in the warmer water species. So that could, a thing that we need to keep in mind when we devise the freshwater fishery management strategy. Well, I think this is pretty much the results related to the big loss and the small gains I want to share with you. But I noticed that this is a quantitative seminar, so I probably want to talk a little bit about the future research and add some quantitative flavor into it to like make the audience happy, maybe. So the future research we potentially want to do is using these preferred days as a metric to like kind of evaluate the impact of climate change on the surplus production of the freshwater fish. And I assume you are extremely familiar with this figure. So supply production consists of the recruitment, individual growth, and the minus natural deaths. So it's not very hard to kind of incorporate their environment factors into a surplus production model and kind of explore their impact. But what is unique for freshwater fishery is that they do not have consecutive CPUE and consecutive catch data. Well, because we have so many lakes, we need to monitor, and we cannot, monitor it in a consecutive way. So usually we have a rotate basis. So this year we selected some of the lakes to do the survey and get CPUE and catch data. The other year we retold to change to other lakes. So this caused the CPUE and catch data for each population is not consecutive. And this figure just shows like how sporadically some of the data we have. For some of the lakes, it probably only survey once for several decades. Some maybe better data quantity. So to deal with this, we are trying to have a like supply production model that could deal with inconsecutive catch and also CPUE. So we know that traditional the supply selection model assume the catch to be accurate, and of course it need to be consecutive to run the model iteratively. So here we try to incorporate our fishing mortality into fishing mortality parameter into the traditional supply production model. And then we could, when catch is available, we assume the observation or error follow normal distribution. And if the catch is not available, the model could still run because you have the fishing mortality parameters estimated, and the model could keep going to kind of calculate the next year's biomass. Well, we did some simulations to test if the model is robust. So here is showing some different scenario of data quantity, like from we only have one catch data and 2 CPU data to we have 5 catch data and 10 CPU data. So these data sets kind of mimic the real data sets I have. So basically, we have more frequent CPUE biological surveys than the Creo surveys for catch data. So the figure on the left shows the estimates of fishing mortality compared with the real fishing mortality in their simulation. So it kind of not follow really well the fishing mortality over years, right? But interestingly, on the right, it shows the figure on the right shows the depletion rate. So it's biomass over K. It kind of estimate pretty well for the terminal years ratio of B over K. So to me, it kind of like the model is trying very hard to estimate the fishing mortality, but fail to accurately estimate them, but end up with a very okay or more reliable estimates of their depletion rate for the terminal years. So the terminal years depletion is quite important. So I assume that the biomass over BMSY shows similar patterns here. So B over BMSY could use as their reference points. So this supply production model could potentially deal with kind of theoretical catch and CPU data in our simulation. So this is just shows the comparison between the estimates and the true value of the terminal years depletion rates. So it goes better, I think, when we have like more than 3 years catch and 6 years CPUE. And interesting, it does not increase that much from here to here. So which means we probably do not need that much data in supply production model. Well, with that, I think that's all I want to share today with you guys, and I am happy to take any questions if you have any. Thank you very much.
Online folks, feel free to submit questions, and people in the room just yell out questions, but if you can't hear, I can repeat the question back. I got a question. Is there good data, or do you have a good sense of the warm water fish growing more rapidly or being larger in size over the past decades?
That's a good question. So actually, the results of our study is showing that the warm water species habitat are increasing, but that that much, not too much, right? Compared with the decreasing of. So yeah, I have no answers on that. Yeah, but generally people are seeing bigger and faster growing fish with the temperature increases in freshwater fish, but people also seeing like decreasing in the fish growth. So it's mixing information, I think.
Thanks.
I don't think you can listen.
Those are the mics.
Okay.
So
Okay.
can you hear? Luoliang?
Can you hear me?
I can hear you, but I cannot hear anybody else.
Okay. Okay. Well, I have two questions actually. One is more general, and is I'm ignorant regarding U.S. inland freshwater, of course. So, what about the introduction of new species? Is that something that happened, and how can this affect your main picture? And the second one is in this simulation study. Maybe I missed something, but so what about the process deviation? I mean, you are trying to fit a model on a system where you are also trying to identify the change on the system. So have you include any change in the production response for this simulation study? Because this can eventually then well, change your ability to estimate your quantity.
Thank you. Thank you very much. I think the first question is related to invasive species in freshwater system.
Yeah, I don't know how it's common. Yeah.
Yeah, I think it's common, and it is something that we are trying to prevent happening. Like the invasive species, not just the fish, right? Other animals that could invade the system. Like here, the most profound problem is in the invasive species. The invasive species is the zebra. Well, what's that species? I cannot remember. Well, sorry. So the invasive species just beyond the fish. So it could be invasive by, you kayak this lake and without washing it thoroughly, and you go to another lake, and it could bring the invasive species into another lake and probably can damage the ecosystem. That is something we prevent happening, but it is a problem here. So, but here we're focusing on fish. I mean, the fish is not that as easy as the marine fish that can move latitudinally. That is the point I was making at the first beginning. But yeah, it could move in lake even. Sorry, I don't quite get the second question. Could you rephrase it a little bit?
Is it just in your simulation study you did, or you are considering to incorporate some deviation in the production function during the time?
The deviation in production function?
Yeah, that can be not stationary over time.
Oh, okay. Yeah. So that's right. So we're trying to estimate the impact of climate change on the supply production. So in the simulation, we do incorporate a parameter that affect the supply production linearly. So our assumption is that with warming, it either increases supply production or either decreases supply production. So that is something we incorporated in the simulation study to try to test if the supply production could estimate that climate change impact the parameter well, even with very limited catch and speed data. Yeah, but I didn't show that result here, but yeah, we did that in the simulation.
I have a question. Hi, thank you for your presentation. My name is Taki. Do you hear me?
Yes, I can.
Cool. So you were showing the thermal performance curve for the optimal temperature for the range optimal for the fish. And so I know that this can look differently for different responses, like I don't know, growth or survival or whatever, like any other type of response that you can measure. Which response did you use or took into consideration as the most representative for the well-being of the fish?
Yeah, right. That's right. So when we considering which thermal metrics we want to use, it actually takes bit longer than we expected. You know, on the course of the fish ontogenetic development, it may require different, you know, thermal, different temperatures, like the optimal egg development temperature, the temperature for the spawning Q that are different. But here we only choose the FTP, the final temperature preferendum, to represent the fish preferred temperature. First, because it's actually what the fish preferred, because they go there. So we assume that if the temperature existed in the natural environment, the fish will go there and stay there if there is no other environmental restrictions. And secondly is the FTP is quite close to the optimal temperature for growth. So we believe that if the fish stay there, it is good for their growth. But it's really not related to kind of related to their you know, spawning. And presumably, if a fish stayed at FTP, it will reduce their mortality and will increase, of course, the survival rate. Yes. Do I answer your question?
Yes, perfectly. Thank you so much.
I have another question about the general lake model. Never heard of this model, so it's very simple question. So you're parameterizing with some data, and you can have like daily estimates of temperature for, is it stratified? Is it like for the old? I didn't really get what are the outputs of this model.
Yeah, thank you for the question. So I'm no expert of their general lake model, but based on my understanding that the meteorological data that is the observed data, because it's the historical handcasting. It's not projecting. So we know for each day at the lake surface what its temperature is, right? And we know like the wind speed, humidity, snowfall, but maybe not as the resolution may be coarser than lake, but we kind of know that information. And that information is incorporated into this process-based model. So for example, what energy is accumulated based on the zonal radiation, and how strong the mixing is based on the wind speed, those kind of process, and they run this huge model and estimate their daily temperature profile. Yeah, that is my understanding of this mechanism model, but maybe not very precise.
Okay, so the outputs you're using is one
The output
resolution. this temperature per.
Yeah, the resolution. So I think the model is able to produce the temperature at each layer, which is every 0.5 meters at the hours basis. But we do not use that resolution. We just use daily average for each depth.
So you have temperature by depth. By day.
Yeah, we have temperature by day for each depth of the lake.
Okay. I have a question too. I was wondering, since there are lakes and they need some freshwater supply, so do you think also the change in temperature could be also driven by the lack of freshwater input? Like rivers, precipitation, something like that. Can you hear me?
Yes. So yes, thank you. So I think your question is the supplying of the water to the lake.
Yeah.
Maybe it could impact their temperature.
Yeah, temperature, also distribution of the fish, even food supply.
Yeah, I think that is factor could affect their lake temperature and food supply. Yes, like nutrition, and also, yes, I agree with you. And I'm not sure how sophisticated the general lake model we have now that are not accounted for that factor. I'm not sure about that.
Yeah, well, for future studies then.
Well, if there's no more questions, I think this is a good time to wrap up Quantum. Thank you again, Luoliang, and thanks for everybody for coming.
Well, thank you everyone. Thank you everyone for your listening.